Right, now moving on to differential equations, which are deemed to be linear equations with constant coefficients. So let's start by considering the equation y equals ae to the px plus be to the qx. This, of course, is not a differential equation, and a and b are some constants. Right, from this, we can just rearrange it slightly to give us ae to the px equals y minus be to the qx. That takes us that far. So let us differentiate the original equation, which is the one up here, with respect to x, and we will get dy dx equals pa times e to the px plus qb times e to the qx. And in the next step, what I've done is replace the a by what we found just up here. So that is b bracket y minus be to the qx plus qb e to the qx. And tidying that up a bit, we get this equation here, dy dx equals py plus q minus p be to the qx. And from this, we can say that b times q minus pe to the qx equals dy dx minus py. So that's directly from here. So we're up to here now. Now differentiating again, so we'll get d2y dx squared equals p dy dx plus q times q minus p be to the qx, which equals p dy dx, and now we'll substitute what we found for b over here and get q into dy dx minus py. And finally, tidying all that up, we'll just get this expression here, d2y dx squared minus p plus q dy dx plus pq times y equals 0. Now this last is called a linear differential equation with constant coefficients. In other words, the coefficients don't have x's and y's in them. And its general solution is y equals a times e to the px plus b times e to the qx. So we're down to here. A and b can be found if some initial conditions are given, but we'll concern ourselves with that further down the road. Now, the method of solution is what's the main concern for you here, if you're given an equation like that. And we're going to do this or illustrate this just using examples. And I made a note here that the underlying theory is omitted, as the important thing as far as you are concerned is of chief concern if this is your first acquaintance with this particular topic. Okay, now just say a note here. If the right-hand side of the equation is 0, the equation is called homogeneous. Some people pronounce that homogeneous, but I prefer homogeneous. Okay, at this stage, we'll confine our attention to just this particular case only. All right, so let's look at an example here. Example number 1, and we'll try and find the general solution to the equation d2y dx squared minus 6dy dx plus 8y is 0. Now the method here, and this is going to take some believing, but I don't want to bog you down with too much explanation at the moment. I want us just to concentrate on how it is done. So we will replace d2y dx squared by m squared, dy dx by m, and y by 1. And this will give us an equation in m here, which is m squared minus 6m plus 8 is 0. So we're down to here. And this is known as the auxiliary equation. Now, that's just an ordinary algebraic equation, which can be factorized. And the factors here are m minus 2 times m minus 4 equals 0. So m is 2 or m is 4. And the general solution can then be just written down as y equals ae to the power 2x plus be to the power 4x. Said earlier, a and b can be found if certain initial conditions are given. And you need two conditions because we have two unknowns. So the method I claim here is quite easy to perform, even if the underlying reasoning has been left obscure. And I've done that quite on purpose. Okay? So let's look at an example, a second example here. This time it's a third order equation, d3y dx cubed minus 3 d2y dx squared minus 4 dy dx plus 12 equals 0. The method is exactly the same. So the auxiliary equation will become m cubed minus 3m squared minus 4m plus 12 equals 0. We can factorize that. I won't dwell on the factorizing. I think most of you should be able to do that reasonably easy using the remainder theorem, using trial solutions. Okay, and that factorizes as m minus 2 times m plus 2 times m minus 3 equals 0. So m will be minus 2 from here, plus 2 from there, and 3 from here. And the general solution will have three parts to it. So that's y equals ae to the minus 2x plus be to the plus 2x plus ce to the 3x. Right, now this is just the first beginning of it, okay? What happens when the auxiliary equation has repeated roots will be dealt with later. And if it has complex roots, likewise, we'll postpone that to a future session, okay? Also, what happens when the equation is no longer homogeneous? In other words, it has a function of x on the right-hand side, okay? We'll deal with that again separately. Now, I've just listed a few practice questions for you here, so I'll leave this up for a few minutes if you want to copy this down and have a go at it yourself. There's no great complication here, so good luck with solving them.